What we're going to look at today is a variation on creating datum reference frames, and this is based on a concept called datum targets. With datum targets, we're going to specify a region or specific location, and to understand how to use these, we'll have to start off with understanding how to construct our fundamental three-plane datum reference frame that we've seen before, based upon a set of datum targets, and then how would we go about establishing the datum reference frame as we did with the regular datums that we've seen previously. Well, first of all, you might ask, why do I need datum targets when we've seen datum surfaces and datum features serve our purpose quite well in establishing a datum reference frame? Well, sometimes we have specific processes such as forging, sandcasting, weldments, as well as others that create irregular surfaces. And when that occurs, it might be difficult to establish a datum feature based upon those irregular surfaces. So what we could do is go for a specific region, an area, or a line, something that could form a line such as an edge, or a specific point on the surface that we know is dependable. If we're going to do that, we might also identify where a locating pin might appear, perhaps in a fixture or in some type of inspection process. And if we're going to do that, then we have to give it a position and a size. So before we can use our datum targets, we need to understand our three-plane reference frame. So when we constructed from three planar surfaces our reference frame in the previous discussion, what we were doing is geometrically describing a plane, and as you know, the general equation for a plane looks something like this: ax plus by plus cz plus d equals 0. Now, if I look at the coefficients of a, b, and c, they represent this direction vector of the plane. In other words, it tells you how the plane is oriented in space. D is going to tell us something about the location of the plane with respect to the origin. So I have the orientation of the plane and I have the location with respect to the origin. Of course, if they're normalized such that this is a unit vector, then we think of ABC as being the unit normal vector. Well, getting back to our primary datum, if we consider a primary datum plane in this case, we can determine this normal vector to that plane by taking the cross product. As you know, if I have two vectors here representing 3 points, if I cross these two vectors, I'll end up with a vector perpendicular to those. So V1, let's say V1 is that vector, V2 is this vector. I cross these two, and as you recall, this is how we would take the cross product, the determinant, with the YZ coordinates, ZX coordinates, and XY coordinates. Of course, K is the unit vector representing the Z-axis, J the unit vector representing the Y-axis, I the unit vector representing the X-axis. And now I've got my vector NP. If I calculate that with actual values for the points, now I've got this vector corresponding to the normal to the plane. And then to solve for D in our original equation, ax plus by plus cz plus d equals 0, all I have to do is select one of the 3 points and substitute it into the equation and solve for D. So now I have my primary plane. Also note that it's completely unrestricted. Because it is the primary datum, there's no influence from any other features in terms of establishing that datum reference. But now when I go to the secondary plane, now I do have a constraint that has to be taken into account based upon order. So what we'll do is we'll take the cross product of any vector in that plane and the primary normal vector. So here you can see this constraint of the primary datum on the secondary datum. So here is NP. That we already calculated that. And here is any vector in this secondary plane. By any vector, we really mean any 2 points. So I've got 2 points here describing this vector V3. And if I cross that with NP, then I'm going to get a vector NS perpendicular to that plane. And of course, we calculate the cross product in the same way. We also calculate D in the same way. We substitute either one of these points to determine D. And now I've got a secondary plane that is perpendicular to the first plane. And then finally, the tertiary plane. Here we have to take into account the primary and secondary constraints on the tertiary. So for the tertiary, all we're going to have to do here is take the cross product again, but we'll just use the primary and secondary normal vectors. In other words, we don't have to know anything about the third plane to find out its orientation. So we already know NP, we already know NS, and therefore NT will be perpendicular to these two vectors. So what do I need anything on the surface of this third plane? What do I really need? Well, we need a point. And why do we need this point? We need the point to determine D, right? So in our ax plus by plus cz plus d equals 0 equation, we still need to know the value of D. This will give us the values of A, B, and C because it corresponds to the normal vector to the plane. Now I've got 3 planes constructed to form my datum reference frame. Well, how could I use datum targets in that context to construct that 3-plane system? Let's take a look at how we would observe the datum targets in the design specification first, and then we'll see how we'll put them together to construct that 3-plane system. We're going to identify regions on the design, or points, lines, and if you see a symbol like this, it's telling you you have a datum target. On the top of the circle, if there is a number there, it's going to represent the target size. On the bottom, we see our datum identifier as before, and then we could have multiple targets to establish that datum, and so we have a number, and there could be multiple datum targets for one datum, and we'll see why a little bit later. You might also see this X here indicating a point symbol attached to the datum target symbol. So let's look at a very simple example. Here we've got a surface and we want to specify regions or point or line. For a point, typically what you're going to see is a location on the surface. So we've got a specific location on the surface that will correspond to our point. And then edges, cross sections, axes, we could specify as a line. So here you can see we have an edge corresponding to the edge of that surface that we want to use as a datum. Or we could use a small region, and the size of that region is described, as we said before, in the top. Here we see it's circular with a diameter of 0.3. Well, if we use datum targets, we can combine them in many different ways. And here are some examples of what you might see. So for the primary datum, there's a variety of ways in which we could establish that datum reference frame based upon the 3-plane system. As we saw in our equation, we could just use 3 points, or we could use a line and 1 point, or an entire region, or 3 regions representing 3 components of the plane, or 2 regions, and again, this is not an exhaustive list, but it gives you an idea of how they might be combined. For the secondary datum, we might take 2 datum target points, or a target line. And finally, for the tertiary, we might take 1 datum target, a point or region, again, telling us something about where that tertiary plane might be. So let's look at an example on an actual specification. Here we've got as you can see, a position tolerance that is being used to control the location of this through hole here. And now we have to think about the datum reference frame as specified here, A, B, C. Well, first we note that A looks to be a typical datum. It is the bottom of the plate here, corresponding to this surface. So we can construct that and establish it using a surface plate as we did before. But now when we get to our datums B and C, we also see datum targets. Now note that the reason why you've got these datum identifiers here is to identify the features, in this case 2 surfaces, that we're going to construct datums for. The addition of the datum targets gives you more detailed instructions as to how that datum will be established. So for instance, for B, we see 2 points, and those points show up both the top view and the side view here. And it gives us a basic dimension telling us where those points are. So now I can determine these points with respect to a distance, and here again a distance, here again a distance from here, and then from the side you can see that we want a point in the midplane, and that's indicated by basic dimension here. We also do that for B. So we're being very specific about the points we're choosing to establish, first of all, the secondary datum reference, and that's going to be done with these 2 points. And we saw previously when we constructed the 3 planes, that's all we need are 2 points for the secondary. And then for C, we only have 1 datum target, and we saw why when we constructed the tertiary plane, we only need 1 point to determine the value of D in AX plus BY plus CZ plus D equation. So you can see we can get much more specific about where we're going to establish our datum reference, and again that goes to specifics about what we expect the surface of these parts to look like after our manufacturing process. So at this point you should understand when you have a datum target, what it looks like, and also how to identify it in terms of its symbol. The target number, I can have 1 or more target numbers. They are going to be combined together to form a datum depending upon the nature of that datum. So in summary, it's not frequently used, but you might see it, and when it does appear, usually you're thinking about an irregular surface. The datum targets can be combined to create a datum reference frame, as we saw, based upon this notion of 3 points for the primary, 2 points for the secondary, 1 point for the tertiary. And 1 or more datum targets can be combined to create that datum in a feature control frame.